Assalamualaikum. We are from Group 3. We'll be presenting OEL 3 proposal on distillation column. First of all, for the problem statement, as we know, distillation is a dominant separation process used in chemical process industry. Poor column efficiency will cause reduction of product purity due to decrease of reflux ratio of the column. This will reduce the degree of separation, which hinders a higher purity of distillate to be obtained. Thus, it is essential to determine the optimum reflux ratio to give most efficient distillation process. In this experiment, there are three main objectives, which is the first one to plot the refractive index against mole percent ethanol in the ethanol water mixture. Second one is to determine the overall column efficiency. And lastly, to discuss the factors that could affect the efficiency of the column. The variable of the experiment. The first one, manipulated variable, is boil-up rates power. Dependent variable is the refractive index or distillate composition, and the control variable is the feed mixture.
Next, I will be presenting on the experimental procedure. For the equipment setup, first make up 10 liters of a mixture of 50 mol ethanol and 50 mol of water. Second, set the equipment to operate at total reflux by switching off the reflux ratio timer on the console. At total reflux there will be no feed or top product or bottom product. For the operating procedure, firstly, set the power controller to 80%, then maintain heat as reflux is introduced to give steady bubbling on all tray and total reflux. Open valve V10 to allow condensate to return back to column. Leave the apparatus for at least 15 minutes so that the system can reach an equilibrium condition. Measure the boil-up rate by performing a time volume collection. Operate valve V3 so that all the condensate is diverted into a measuring cylinder. Take a small discarding sample of 5 to 10 ml into an alternative vessel. Divert the condensate into the measuring cylinder and use the stopwatch to measure the time required to collect 15 ml sample. Repeat procedure A until B 3 times and take an average value to determine the boil-up rate. After sampling, measure and record the refractive index (RI) for the overhead samples taken. Take a sample of the bottom through valve V2 and record the refractive index. Repeat this procedure, step 3 until 5 every 10 minutes until 5 samples of both overhead and bottom are obtained. Record temperatures T8 and T1 to calculate the average column temperature. Repeat this procedure 1 until 7 for boil-up rate at 100% power. Develop calibration curve to determine the concentration of the components in the taken samples. Then, at the time, measure the refractive index of the 25, 50, and 75% mole of ethanol per water mixture. Measure the refractive index of pure ethanol and water. Then plot a graph of refractive index versus small percent ethanol in the ethanol water mixture. The results obtained from this experiment allow the mixture composition to be determined from a measurement of the refractive index. Next, for calculating relative volatility of bottom and overhead sample, use the following equation. Continue with the calculation of the number of theoretical plates for each reflux ratio and determine the efficiency. And lastly, plot a graph of distillate composition against the number of theoretical plates for each reflux ratio.
Data and expected result. As you can see there, I include the table with the required parameters, and there are also graph of number of theoretical plates versus distillate composition, where the result shows an increasing trend, which is based on the expected data. Based on the tables, it shows that the boil-up rate increases as the power increases, as well as the pressure drops. This is because more vapor went up the column against the same liquid that was already flowing down as the power input increased. It is because of the excess vapor increased resistance as it tried to rise up the column. The vapor flow rate therefore created a larger pressure drop. Besides, since a greater flow rate was produced by increasing the input power, the column efficiency is expected to increase as a result, since better mixings and separation is expected from a higher flow rate. The mole fraction of ethanol in liquid phase is expected to be increased with refractive index. It is due to the concentration is higher, which causes more light to bend as the medium is denser. When the XA, which is the mole fraction of ethanol, is 0.24, it shows that it had the largest error bar as the value deviates the most from the average value. In order to improve the calibration graph, the refractive index of a larger concentration range with a smaller interval should be identified.
Ethanol is considered hazardous by 2012 OSHA Hazard Communication Standard. According to MSDS of ethanol, some precautions are needed to be considered while handling and keeping the chemical in storage, such as firstly, wear personal protective equipment or face protection. Next, ensure adequate ventilation. Then, do not get ethanol in eyes, on skin, or on clothing. Avoid ingestion and inhalation. Keep containers tightly closed in a dry, cool, and well-ventilated place. And last but not least, keep away from heat, sparks, and flame as ethanol is flammable. Example of PPE is chemical safety goggles, protective gloves, noise respirator, and practice good hygiene. And that's all from us, Group 3. Thank you.